Yes, you can.
Great. Yeah. So just mute, the streaming microphone. Okay. So thank you, Professor Sum, for accepting our invitation to speak at the Subsurface Mechanics webinar series. It is really a pleasure to have you here. And I would like to request Professor Jitendra Sangwai to formally introduce you as the speaker of our series today.
Thank you, Chandra, for starting the seminar. Let me introduce Professor Sum. Professor Amadeu Sum is a professor in the Department of Chemical and Biological Engineering at the Colorado School of Mines and leads the phase to flow laboratory. He holds BS degree in the chemistry and chemical engineering and MS in chemical engineering from Colorado School of Mines and PhD in chemical engineering from the University of Delaware. He did postdoctoral work at the University of Wisconsin-Madison. He is a DuPont Young Professor recipient. He has been working with clathrate hydrate research for over 25 years, covering experimental, theoretical, and simulations topics of hydrates in flow assurance and science. Example, phase equilibria, kinetics, deposition, chemical inhibition management, interfacial phenomena, multiphase flow, spectroscopy, and molecular simulations. More recently, his flow assurance research has also included wax and asphaltene formation. He is author and co-author of about 190 peer-reviewed publications, a recent book on hydrates in flow assurance, and creator of 2 inventions. He has worked closely with industry, including Hydrate Joint Industrial Program and a DIF staff. Presently, he leads the Joint International Research Program on Gas Hydrates and Multiphase Flow, partnering his group at Mines, École des Mines Saint-Etienne, France, and Federal Technology University at Paraná, Brazil. Professor Sum is one of the really leading researcher in the field of gas hydrate, and I'm very thankful to him for accepting our invitation. He quickly replied and say that he will be very happy to be giving a talk in this webinar series, and his presence in the webinar series has really made us happy. Thank you, Professor Sum, and I invite you to start your talk on the multiscale-multiphase approach to gas hydrates, learning and solution from lab to the field. Professor Sum, please. Thank you.
Thank you, Jitendra, for such a nice introduction here. And I want to start off by thanking especially Professor Jitendra for the invitation, for this opportunity to present and share with you some of our learnings in here and what we've been working on the gas hydrates. It is certainly a very challenging time for all of us with the pandemic and being able to connect halfway across the world in here has been perhaps one of the good sides of the pandemic that has eased our connection with colleagues and the people who we typically wouldn't have the opportunity to talk to. So what I want to do today here, it is present to you and give you some ideas about how we approach our research and how we consider gas hydrates. But before I do that, I just want to briefly introduce the university that I'm not quite sure many of you might know the Colorado School of Mines, but we are a relatively small university. We are close to celebrating 150 years. We only are about 6,000 students, about 4,600 undergraduates with another about 1,400 grad students. We are very focused in the science engineering, and we are located here in the beautiful foothills of the Rocky Mountains, and that's the view that you see here. There's this mountain right in the backdrop of the university with this M, and this M stands for mines. And we have a mascot in here that's burro, and that has one of the traditions associated with the mining back in the days when the university study. And as you see, this picture here was taken during winter snowstorm day. That we also have the blanket for the Denver Broncos. That's the football team here in Colorado. But more interesting about this M is that it gets a treat every year right around this time of the year when the new students, the freshmen that start in the university, they get to get a hard hat and bring a 10-pound rock and walk from our campus all the way up to the mountain, and that's about 3 kilometers, carrying this rock, so that they walk with the president. This is our current president of the university. And then they sit on the M, lay their rock there, and then the older students throw white paint on the freshmen. And this is sort of the tradition, the initiation of the students here at the university. And you can see them all then covered with white paint. So it is a nice tradition and something that everyone looks for at the beginning of every academic year. I want to start off by acknowledging our collaborators and sponsors. We work with a number of different academic groups at other institutions, and this is a list of all of them that we've been collaborating over a number of years. We're very fruitful discussions and collaborations. And there are our sponsors, this mostly from the industry, or the traditional oil and gas companies. And certainly there's the people who have contributed significantly to what we have done. These are grad students and postdocs that over a number of years have generating the knowledge and advance the research. So let me start off by some key ideas here that I want you to keep in mind as I go through my presentation, with the focus on gas hydrates. I hope to demonstrate to you that the gas hydrates are a rich area for science and engineering. Gas hydrates are far more complex than ice and water structures. We really need to think gas hydrates as a porous mixed medium, and that's in a way maybe one could think about that, but it is not widely accepted yet, this idea. And so I want to emphasize, and the properties of gas hydrates, the last one in here, really highly depend on the formation conditions, and that it is sometimes difficult to make generalizations because it is very specific how they are formed. Okay. So let me start off by showing you this picture in here. Then there may be some who are not familiar with gas hydrates. So I'm starting from the very fundamental aspect of what gas hydrates are. And what you see here it is that someone light up what it looks like a snowball, but it is actually a gas hydrates, and it is sustaining its own combustion in here because of the gas that's trapped and that is being released on the dissociation of the gas hydrates. So you can see it, that burning snowball, if you will. And this very dramatic picture in here, this person holding this hydrate and it is burning, but it's not burning this person's hand because the hydrate is melting, and the byproduct, it is the gas that's sustaining the combustion, and the water that you see dripping from this person's hand, it is cold, so it doesn't burn this person's hand, right? But what are really gas hydrates, right? There are 4 ingredients for gas hydrates. You need water, you need some gas, and the right temperatures and the right pressures. And then under those conditions, water will self-assemble around the gas molecules. And depending on the size of the gas molecules, you're going to form different cavities. And depending on the size of this gas molecules, these cavities that are formed can come together to form what is known as structure 1 most commonly, or structure 2. Those are the two most common crystal structures for gas hydrates. They have the combination in a specific pattern that are identifying these crystal structures. Now, what is unique about gas hydrates is that it's mostly water. By and large, you have one molecule per cage. There are exceptions in here, such as very small molecules as hydrogen and nitrogen. This is considered as inclusion compounds. Another unique property of gas hydrates is that it's non-stoichiometric. What I mean by that is that when you see these different cages in the crystal structure, not all of them needs to be occupied. Some of them can be vacant. And so this gives this non-stoichiometry of this compounds. Now, if you were to take one volume of a gas hydrate and dissociate that, you would end up with about 160 times the volume of gas at STP and about 0.9 of that volume in water. So there's a very significant amount of gas that's stored and trapped in the hydrates, and that's one of their properties that has also consequence for different types of applications. Here you see a list of different gases that typically form gas hydrates. And as you see, there's low molecular weight gases, some of the hydrocarbons, some of them are the inert. Now, this is just expanded in view here of the water cages and the hydrate structures, and how you go about in forming structure 1. That's the combination of these two types of water cages. Structure 2 is a combination of the blue and the green. And then there is this other cage here that's denoted as structure H. That's a combination of the blue, the purple one, and the red one. That's much larger, and then it can accommodate a significant larger types of molecule. This is structure 1 and structure 2 are very common and mostly found in the man-made and nature, but structure H typically is not found in most applications. Now, and the structure in here, it is determined by the size of the gases, right? And this list in here considers in structure 1, structure 2, and structure 2, the pure formation of the hydrate from a single component. But of course, you can have a mixture, and then there would be a distribution of these gases in the cages that make up the hydrate structure. One interesting fact is that structure 2, it is formed with the very small molecules like hydrogen or helium. Structure H requires a small molecule like methane or xenon in order to accommodate these smaller cavities, but you see it can accommodate this very large types of molecules, depending again on the molecular diameter, and that's what's going to determine the crystal structure. Now, let me give you my view of the world of gas hydrates and how I think about them in terms of their applications and the fundamental aspects of it. There's the good side of gas hydrates, and the good side of it has to do a lot with the natural deposits of hydrates, mostly offshore, oceanic environments, and certainly India has a lot of interest in developing the technologies for the production and recovery of gas from those natural deposits. And by estimates, the amount of gas that's trapped in gas hydrates surpasses all the other combined resources in terms of carbon. And so it's a very, very large resource there that can provide a significant amount of natural gas. So especially countries in Asia like India, China and Japan and Korea are very aggressively going after the exploration and the recovery of gas from these natural deposits. Now, I showed you that there's a significant amount of gas trapped in the gas hydrate. So it has been also been looked for energy storage due to the ability of selectively enclosing certain gas into the crystal structures. Gas hydrates has also been considered for chemical separation, including desalination. And there has been also some interest, for example, of using clathrate hydrates in here for hydrogen storage, as we consider more and more the use of hydrogen as a potential energy resource. There's the bad side of hydrate as well. And that has to do with what happens in the oil and gas production. One needs to manage gas hydrates. There are certainly approaches of avoidance, but more and more industry is moving toward the management. Gas hydrates is a solid precipitation phenomena that occurs during normal hydrocarbon production. And one needs to consider what are the consequences of the impact of having hydrates in the system. So a lot of it is in the avoiding and preventing catastrophic scenarios that lead to the ugly side of hydrate, right? This is a famous picture that has come from Petrobras. This is not a complete hydrate plug that is being removed from a pipeline offshore. Certainly there is a lot of ice and trapped water, but you can get an idea in here on what is the consequence of having such a plug formed and the downtime associated with it. And there's a safety issue as well, that pressure can be built up if this is not dealt with in the timely manner. And the other ugly side of hydrate is that because of most of the gas that's trapped in these natural reservoirs is methane, and methane is a greenhouse gas, much worse than carbon dioxide. And especially in the permafrost, there's also a significant amount of hydrate, and there's concerns about the melting of those hydrates, and if they get into the atmosphere, that can speed up significantly the global warming and climate change that we all already experiencing. And there's the beautiful side of gas hydrates, and the beautiful side in here that I say has to do with water. Hydrates are mostly water, and to this day, water fascinates us into what it does. And it is even more beautiful in here because it's not just water, it's water in combination with some other molecules, and there is a number of different things that we want to learn about in terms of nucleation, of dissociation, structure composition, inhibition, and metastability. And I will show you some of the work that we've been doing here just to address this beautiful side of the nucleation as well. Okay, so there's the good, the bad, the ugly, and the beautiful for gas hydrates. Now, our particular group in here, in a way, it is very diverse in terms of the depth and the breadth of what we do on the fundamental side and also on the application side, with a combination of experiment, modeling, and simulation. So we really take this multi-scale and approach and looking at the very fundamental to the very applied in terms of how we deal with gas hydrates and how we try to understand it. Right? So the first part in here has to do with when do gas hydrates form, and we are going to look at the basic thermodynamics. That's always the starting point. The thermodynamics is essential for us to define the conditions that we would have hydrates forming, right? And so typically what we do is look at the phase diagram for a gas hydrate, and here on the left side they give you the phase boundary for these pure hydrates that would be formed from nitrogen, methane, and then ethane and propane. And so these points are actual measurements that have been published, and the solid line is just a prediction that shows a fairly good agreement. If you are on the right side of this curve, on the bottom, there's no hydrates, and then if you cross this boundary here on the left side at the higher pressures, lower temperatures, then you have hydrates being stable. Right? And so it's important for us to define this set of temperature and pressures, because then we can determine when hydrates will form or not. And as you can see here, the conditions that I show in this scale, they're all above the normal freezing point of water, right, or the melting point of ice. So hydrates are stable even at above the freezing point, but it does require some pressures that you see in here, typically for most of the gases that form hydrates. And these are for mixtures, right? You can predict what are those phase boundaries, and depending on the gas mixtures, for natural gas mixtures. And these are based on a very robust model that has been developed over the years that's very reliable. And that has to do with considering how we learn in fundamental thermodynamics the quality of chemical potential of water. So this model developed by van der Waals and Plateau back in the 1950s, and it relates the chemical potential of water to the occupancy of the cages with the gas molecules. So we can calculate what is this occupancy by considering something similar to a Langmuir adsorption that you might have learned in your courses. And from there, we can then determine what is the chemical potential of water in the hydrate phase, right? In the hydrate phase, and then in this, the pie here considers either liquid water or ice, right? That we know how to calculate from the changes in temperature, changes in pressure, and how that impacts the water activity. Okay, so in this formulation does allow us to make this sort of predictions, and this has shown, and it is reliable, and it works really well for uninhibited systems. When I say uninhibited system, it means that it's just fresh water. But when you consider inhibition of gas hydrates, this is the same thing as lowering the freezing point of water, right? We can add salts or alcohols or glycols to water to lower the freezing point, and we can do that the same thing for gas hydrates. So we are shifting those boundaries that I showed you, and I will give you another example here. And all that has to do is with that you learn in basic thermodynamics to this water activity. So if you are able to determine how much this inhibitors impact the water activity, you can determine what is the suppression temperature. Now, over the years, we have developed a reliable correlation here that we denote as Hu-Lee-Sum correlation in order to account for that. So this correlation accounts for any mixtures of salt or in combination with the typical thermodynamic inhibitors that we are typically use, like ethanol, methanol, or glycols. And we can determine this water activity simply from this correlation, and then determine what is this shift in the equilibrium boundary. And this is what we have done in order to show you here the results of our correlation to this measured data. And so as you see here, it works really well. This is the data for the fresh water. What I'm showing you here is actually there is a very simple way that we develop as well in order to determine this shift that has to do with a single measurement. Instead of making, like for this case, 5 measurements, I can make one very simple measurement of the ice melting point. And this is done using typically a DSC, a differential scanning calorimeter, at atmospheric conditions. And so if you have that value, you can use that in order to obtain what it would be the temperature suppression in here for the gas hydrates. And so this is one of the innovations that we have brought recently that has essentially eliminated the need to make this very time-consuming, expensive measurements at a very high pressure with one single trivial measurement that most people have access to a DSC. Now, let me move on and tell you a little bit about how gas hydrates form at the microscopic level. This is just going to spend a few slides in here to show you what we can learn and what we need to learn about how hydrates form at the molecular level. And the tool that we use in here are the molecular dynamic simulations. And we've been working with this for a number of years. And these are 2 of the most recent papers that we have published on this that look at the process of gas hydrate formation for propane and for mixtures of methane and propane. Right? And we can track the evolution of the system over time. And from the point that they start initially completely disordered to the point where they nucleate, and then we see some growth, and then we see some ordering or transformation over time. Right? And this is what I show you here in this video. Let me change in here. This is for one of the simulations. Sorry, it's not playing. It's just very slow. I hope this doesn't crash my computer. I apologize for this. Yeah, I'm gonna have to move on. Sorry. Apologies. It's something happening here. Always some technical issue. Sorry, I'm not going to play the video because it seems that it is going to crash my my presentation. So let me just go back here, but I apologize again. What we see from those simulations is the evolution of the system to form these patterns that can be identified to what we know is a structure 1 or a structure 2. These are different examples that we have extracted from the simulations. Unfortunately, again, the video is not working, but you would see the evolution of the system from a completely disordered to a ordered state And we can learn a lot in trying to obtain the mechanism for nucleation and growth of these crystal structures. This is still a challenge, and we want to have this insight because if we are able to understand what is happening at the molecular level, we would then be able to better control either the formation or the inhibition of gas hydrates. And so this is desirable. It's something that has not just a fundamental interest, but very practical interest into the use of gas hydrates in many different areas. But let me then move on in here to consider the macroscopic formation of gas hydrates that it is by and large a lot of the work that goes on in this community. Okay. So what is important to understand about the macroscopic formation of gas hydrate, that we need to consider where the water is. What are the different interfaces, right? And I showed this slide because one needs to understand that in the gas phase, if you have a gas phase, the number of water molecules, it is very small. It is about 1 to 10,000. The number of water molecules in an oil phase, right, a liquid oil, is about 4 in 10,000. So not very much, right? Very few water molecules. Whereas the amount of gas in water is about 2 to 1,000, right? Now, when a gas hydrates form, we have this ratio of 1 gas molecule to 6 water molecules. And so if you compare this ratio to any of these ratios, right, there's at least 3 orders of magnitude change in concentration. Now, this concentration of gas in water, it is like that of a miscible phases, right? Miscible components in a phase. And so that's why sometimes for gas hydrates, it is described as a solid solution, right? Because of this concentration ratio. Now, because you need to have, as I stated at the beginning, water and gas at the right temperature and the right pressure, the water and the gas needs to be in contact in order for the hydrates to form. And if you have a solid surface and the water sitting on that surface, you can have the gas or the oil that would be saturated with the gas, and then hydrates would form at that interface. Or if it is the water with the gas, and then that water would convert to gas hydrates. If it is in the bulk, the water is dispersed in the oil, right? Then that would be as a droplet. And then so it would form sort of this film. Or if you have oil that's dispersed in water, and again, the interface between the water and the hydrocarbon phase, right? Or if you have a gas bubble in the water, then the hydrate would form as a shell around this gas bubble, right? So this is a very important concept one considers and try to understand what is where hydrates are formed, right? It always need to be an interface. So let me give you some different examples in here on the actual formation of gas hydrates. And this first example has to do with a system where we have a pipe with cold wall temperatures, and then we have hot gas that's saturated in water. And so hydrates are not going to form right in the bulk gas phase. This water that goes up this cold pipe is going to condense on the surface, right? Anytime that we have water vapor is, there is a temperature gradient that we know we experience. There's a condensation, right? That's what happens when we go take showers, right? In the bathroom mirror, typically we see this fogging up and the condensation of water. And then if the conditions are right, this water is going to convert into hydrate. And this is what you see in here, these water droplets that are condensed, right? And so depending on the set of conditions, right, we're going to set up a convection of this gas in this cold pipe. And then this is going to induce the transport of water into this cold pipe, and over time, hydrates are going to deposit. And then eventually, depending on the conditions, the duration, and the amount of water in the system, it can enclose this cross-section of the pipe that's gas filled, right, and create a plug, and which may or may not be desirable, right? But that can happen. And once you form the hydrates, this is a view of the pipe filled with hydrates. We have a camera that is going down into the pipe that you see that is covered with these hydrates that are very soft like, right? And it certainly looks like ice, frost, right? But it is actually gas hydrates in here that you see it almost closing the pipe with the amount that is deposited. And again, depending on the conditions, this location where you have the most for deposition of hydrates can vary, and that it can go lower or higher depending on the amount of essentially water that you are getting up into the pipe, right? And so it does matter how you form hydrates, and there are many different ways that you can form hydrates. And one of the emphasis that I want you to consider, it is that it matters how you form the hydrates, and the conditions, especially in terms of mixing and shear that you impose during the hydrate formation, will impact that what is the hydrate that you form, right? In this previous case that I showed you, right, this is essentially just due to convection of the gas in this pipe, and then it is a condensation. So there is really no shear that's imposed in the system, and this determines the morphology of the gas hydrate and where it is forming, right? Now, there are large scale facilities that consider shear that mimic the gas, the hydrates that form in a flow line, for example. These are flow loops. The issue with flow loops is that it requires very large volumes of fluids. It is expensive to build and operate. And if it is small in diameter, that many of the flow loops out there are, there's significant wall effects. And then we want to be able to consider what happens to the formation in the bulk, and that can be a challenge. Now, more commonly, what many different research groups use are what is known as a high pressure autoclave. So this is nothing more than a pressure cell that you have at some stir that provides this mixing. So the shear is imposed from this impeller, but depending on the application that you are looking at it, this mixing and shear might not necessarily mimic the right set of conditions. And so one needs to be aware that this type of mixing, whether it's representative and is actually very important to consider the geometry of the system in order to understand how hydrates are forming. The other common system, it is essentially autoclave like in the previous case, except that's coupled to a rheometer, so you can get direct measurements of the torque that could be translated into some apparent viscosity. And there's another piece of equipment that's widely used for gas hydrates studies. And we have one of those systems as well in our laboratory, and that we perform a lot of the measurements. Another very common type of system is what is known as a rocking cell. And this is an illustration. It is, and this is a visual one where they use a sapphire tube, and they have a ball inside that goes back and forth and on the rocking to induce the mixing of the phases, right? And then you can visually see the hydrate formation in those cases. Now, what is, and they can associate the relative viscosity to the travel time here of this ball that as it rolls back and forth in the tube. Now, recently we have developed a new system in here that in a way brings the best of all the previous systems that we have considered with a number of advantages in terms of what we can do to study gas hydrates. And this is what I call a high pressure rock flow cell in order to differentiate from the rocking cell that I just showed you. And it is nothing more than a piece of pipe, and it can vary the diameter and the length. There's a cooling jacket, and this sits on a table that we can control the rocking motion in terms of the angle and the rate. And what is unique about this system is that we put a camera inside of the cell, so we can get these views of how actually gas hydrates are forming, especially if you're considering the formation in a flow line. And in this particular examples in here, you see the hydrate forming on the top of the pipe as well as in the bulk phase. Right, and I will show you some examples in here of the different set of conditions and the resulting hydrates that were formed. And that's why I emphasize that it's very important for you to consider the formation conditions, because in a way you can get almost anything that you want depending how you form gas hydrates. Right? This is just to give you a sense of how this particular rock flow cell operates. This is a visual cell that you see at the top with the liquid going back and forth, and then we use a transparent cell with a different view, and you see the mixing of the phases. The oil is in yellow, the water in blue, and this certainly it is not one-to-one, but has a fairly close representation to what one would expect in actual pipe flow. And then here at the bottom, you see you saw the actual process of hydrate formation. In this particular case, the hydrate formed and accumulated at the bottom and of the cell, and then the liquid that remained flowable, it was just the oil, but it forms like a ice-like, what it looks like, but that's actually gas hydrates. Right. So let me give you here some examples of how hydrates actually form under shear conditions. And in this example in here, what you're gonna see is that the hydrates are gonna form. Right? This is a system with oil, water, and gas at this pressure and temperature that we are forming, and then you start to see the hydrate there that is going back and forth and being carried by the liquid. Right now, what it is very important to pay attention in here is that what it appears to have a significant amount of solid present in the system, that the solid would be the hydrates. But we can determine how much actually hydrates were formed by the amount of gas that is consumed in this process. And if we do that, we have only about 4% of that water being converted to gas hydrates. Certainly what you see there, you would have never guessed that it was only 4%. But what that tells you is that the effective volume of the hydrates is very large, right? And you are not forming this perfect crystals of gas hydrates. And the gas hydrates are certainly expanding. And the best way that I have to describe a gas hydrate is like a sponge, right? And it formed these porous structures with a very large effective volume. And we know from experience and from this observations that once hydrates form, all the free water disappears. But even though we don't see it, and the only way that water disappears because it is trapped into the gas hydrate. So the gas hydrates, again, it's a sponge, soaks up all this water, and this water gets trapped inside of this sponge and doesn't get in contact anymore with the gas, and so it doesn't form, and so you end up with essentially very small amount of water conversion, but you have a significant amount of solids. This is another very interesting case, right, that we have, where you're starting to see some hydrates here, and my title is Expected and Unexpected, right? And you're starting to see the growth back here of the hydrates, and over time, this is a very long experiment. This video is sped up by 1,000 times. Okay? This goes over a day in this experiment. Okay, and then after this is the first 21 hours, the system, there's no mixing, right? But and again, this emphasizes that there are many different ways of hydrates forming, and on the top of the wall in here, and even in the bulk phase. But after 21 hours, we start rocking, and then there's some mixing of the liquid phases, and you're starting to see further growth of the hydrates, right? And over a short period of time, you see this expansion of the gas hydrates, right? And again, there's not necessarily a lot of water being converted. It is just that the swelling, in a way, of the gas hydrates that you see. And then at the end of the 25 hours, you actually don't see any liquid anymore flowing back and forth in the cell. Is part of, again, due to this region that hydrates are sponges, so they trap all this water and then that are essentially soaked up into this porous structure, right? So let me go next in here. And this is an example that's quite interesting, in that you having hydrates form here at the wall, at the gas liquid interface, and I'm going to jump in time. And so you can see that it is growing significantly over time. It's just this swelling. There is only 50% of the water conversion, but you see that this growth of the hydrate in here that essentially encloses the entire pipe. But there are conditions that we can do these experiments where the hydrates remain fairly well dispersed in the system, and that's just one of the cases. You know, this milky liquid that you see has a lot of these fine hydrates, little sponges, if you will, that are very well dispersed, And these, in a way, are ideal conditions when one tries to consider the flowability of gas hydrates. Right? So I really like this particular example in here because it says a lot about the unexpected of gas hydrates and the importance of mixing. Okay. And so what you're going to see here is the hydrates form and then they accumulate at the bottom. And then you see some liquid that is still flowing at the top of it, right? But after some time, you actually don't see any more liquid flowing. But overall, this time the cell, it is continuously rocking. So there's continuous shear in the system, right? And then after some time, you start to see some liquid that's sort of, in a way, trying to being squeezed out of this solid that you see accumulated at the bottom. And again, remember that this is being continuously sheared. And then what you're going to see here as we progress in time is that we're starting to see more liquid and the accumulation of solid at the bottom, it is in a way being broken up and being dispersed in the liquid, right? And then by the end of this time in here, essentially all that solid that you saw, that seemed to be a significant amount, right? But there's only about 38% of the water convert to hydrate. It is very fine, finally dispersed in the liquid. And the point in here is, again, that the conditions, the shear is very important to consider in the process of hydrate formation. And you can get things that you might not expect depending on how you do your testing, right? So I'm going to skip this because except to point out that there's this very important concept that I wanted you to think about, as I mentioned, that hydrates are sponges, right? And so, in India, it's not as easy to experience snow, right? But here in Colorado, we have plenty of it, right? And hydrates are, in a way, very much like snow. And my kids get very excited in the winter when we get this very wet type of snow, right? And that means that there's some free water at the surface of the snow. And with the wet snow, they can make snowballs because they can compact the snow very well and then make really snowball to throw at each other, at me. But a lot of times here in Colorado, we have this dry snow, right? That we say, because it's just like a powder-like, and then there's no free water at the surface. And we cannot make a snowball because it's not going to stick to snowflakes, right? And hydrates is the same concept. It is wet versus dry. You make a wet hydrate if the water from this sponge, from this porous structure, can permeate and reach the surface. And that's going to allow the hydrates to agglomerate and be this large mass. But in the cases where we can seal or keep the water from reaching the surface of these sponges, we have a dry hydrate that corresponds to the dry snow, right? So they won't stick and they won't agglomerate, and then they will be very well dispersed in the system, right? And so we have developed a whole mechanism and theory about this, and I just want to point out about this wet and dry concept, okay? Let me skip that for the time being because I see that I'm just reaching my time limit here for the webinar, and I want to give the opportunity to have some discussions or answer questions, comments that anyone might have. But I want to just end up here where I started. I hope I have shown you that gas hydrates is a rich area for science engineering. There's many different things that one can explore here at the very fundamental level, and many different applications for this very interesting structures. Hydrates are far more complex than ice and water structures, and I say that because we also have to consider the gases, right? The gas that make up the hydrates. I showed you different examples for this porous mixed medium that hydrates are, and I think this is an important concept that more people need to consider when they talk about gas hydrates and what they are. Rarely we're going to form a pure hydrate that has zero porosity. And I hope that I convince you as well that the properties of gas hydrates are highly dependent on the formation conditions. So with that, I'm be happy to take any questions that anyone might have. Thank you again for the invitation and being part of this webinar.
Thank you, Professor Sum, for a very interesting talk. I'm sure there are many questions. We can begin by looking at some of the questions in the Q&A panel. Okay. So the first question is asking you, again, it's a more of a, I guess, given the current environment of climate change and its immediate impacts, it's asking you if the burning of gas hydrates will affect the environment.
Thank you for the questions, and certainly a very interesting question. I suppose the answer there is no more than burning natural gas, right? Because all that you are burning from the hydrate is the gas that's trapped in the gas hydrate, right? So the impact is the same. Now the byproduct there of the gas hydrate is water, right? You have a significant amount of water, so potentially, you want to develop a technology here that might have dual purposes. Maybe have a source for fuel for burning, right, for heating, but also fresh water, because it's essentially pure water that you're going to end up here with gas hydrate.
Thanks for your answer. The next question is asking you, what would be the influence of soil, which is the presence of various minerals, on the micro and macro mechanisms of hydrate formation?
Great question. I think this is a very fundamental question, but a very important one, especially as you're considering the hydrates in the natural environments, right? And it all has to do with where hydrates are, how hydrates are formed, right? Let me try to go back here to my slide. So surfaces, right? The hydrates are gonna form from the water that was initially present at that surface, right? Whichever mineral surface that you are considering, that then got into contact with the gas. And so this is what would happen. And there is still debates on exactly whether the hydrate would be bound to the surface or not necessarily bound, or you would end up with a free water layer here between the hydrate and the surface. So this is certainly something that is still being considered. And I think when it's based on what I showed you as well in this talk, and what I emphasize is that we can get very different answers from the lab based on how we form the hydrate. And so one needs to be very careful under the conditions of hydrate formation. In nature, it is of course very different, because the hydrate had a long time to anneal and to be at the current state, right, over millions of years. Right? At the more microscopic level, minerals, there are salts, right? They can dissolve in water, and they certainly will have an impact into the formation of the hydrates, right? And you can use maybe some of the simulations to try some of that understanding, but certainly water salts are inhibitors to hydrates, right? They can suppress the hydrate formation condition the same way that when you add water, salt to water, and that can lower the freezing point.
Thank you, Professor Sum. So the next question is from Dr. Parul Sahu, and she would like to know for hydrate deposition in gas-filled Deadlegs experiments, what is the cold surface temperature and pressure inside the pipe?
Well, in our experiments, we did mostly at 100 bar, right? And the cold surfaces vary between, I think, 0 degrees Celsius up to 15 degrees Celsius. But the key point in here is that you need to have a temperature gradient in the system in order to condense this water. If the system is at a uniform temperature, you're not going to have water condensation. And so that would minimize essentially the water that's condensed and in turn the hydrates that's formed. In all our experiments, the reservoir here, the water at the bottom, the liquid water, was kept at a higher temperature. The lowest that we consider was 30 degrees Celsius. The highest was 80 degrees Celsius. So the gradient that you set, it is important to establish this convection of the gas and the water vapor in the pipe in order to create this condensation and then formation of gas hydrates.
So the next question is asking you, how do you determine the stability zone for a gas hydrate reservoir? Not sure if that's the intention of the question.
So gas hydrates, right? The stability in here that we determine this boundaries, right? Whether it's a pure component or a mixture, any one that it might be, right, is dependent on the gas composition, right? And if you have inhibitors like salt or any other that is dissolved in the water, right? This, of course, can be measured, or we have these tools that can give us what is this equilibrium boundary, and they are pretty reliable nowadays, the many tools that are available to determine what are these boundaries in here, right? So in a reservoir in the natural environment, right, there's certainly a pressure, a hydrostatic pressure associated with that. And there's a thermal gradient at the bottom, also as you get the subsurface, right, from the seafloor. And so you would need to determine what is the pressure and temperature to determine where the hydrate stability zone is. And those who you work in this area rely on this type of, plots in here to determine under this temperature, as the temperature is changing and the pressure is changing, in which side of this boundary you would be.
Thanks, Professor Sum. There is a question here which is asking you about the various challenges in exploration of gas hydrates. So what are the key challenges as it stands currently?
From my understanding, there are many. There are and the challenges, right, if I can just list a few of them that I see are very significant, right? Now, the distribution of hydrates in the oceanic sediments, it is not, of course, uniform. There is a distribution and there's a lot of sediments there. So they talk about a saturation of the amount of hydrates for a volume of sediment, right? And so is there enough of the gas hydrates in order to be viable and having significant production of that gas? Now you need to dissociate that gas hydrates from the sediment, right? So that there's different options on how to do that in terms of changing the pressure in the reservoir, right? Certainly you could do temperature or pressure, but pressure is much easier to do than trying to increase the temperature at the subsurface, right? There's considerations about the chemical injection as well in order to facilitate the dissociation. And there's the issues also associated with the collection of this gas, right, from the reservoir, and then how you're going to pump this gas from the reservoir to surface, right? And because there's water as well being produced, as well as sand, right, sediment, one needs to take into account that as practical aspect as well. You are going to be producing significant amount of sediment and water, and that might cause some operational issues that must be dealt with. There are certainly a lot more, and I could go on and talking about that for many different for a long time. Yeah, but I'll leave it at that for now.
Sure, thank you. There's a follow-up and a related question which is asking you about your opinion on subsea gas hydrates as a potential source of energy.
Yes, and again, I think a lot of countries in Asia are very aggressive in trying to make this resource viable. And I think it is promising where things are going. And I think as in anything that we have done, not just related with hydrates, but even exploration of conventional oil and gas, back in the days, we were learning as we go along. And I think that's kind of the same thing here for gas hydrates. We are going to learn the more that different countries, different organizations consider that as a source for natural gas. There are, just like I mentioned in the previous questions, there are challenges, but I think we as individuals, as people are very creative in coming up with the right technological tools that we need in order to make this viable. So I think there's great potential there, but it is a matter of also other factors as economics, right? Environmental impact, geological impact, right? That needs to be taken into account, right? And so it's not that simple of an answer, I suppose.
Sure. Thank you, Professor Sum. I would also like to give this opportunity to Professor Jitendra and Ramesh, if they would like to ask a few questions, as it's their area of research as well.
Professor Sum, I have one small question regarding the wet and dry hydrates that you talked about. Now, if you consider, you said that like when the hydrate is a dry, it's difficult to agglomerate, right? I mean, so I was wondering, because if you look at the surface of the hydrate, like ice, for example, it becomes a sticky, So if you really connect two ice block, over a period of time, they get connected to each other. So I hope that even if the hydrate is a dry, don't you think that they will try to agglomerate even if the absence of water level around the surface?
No. If it is dry, there's nothing that will make the hydrates bind.
So the surface is not sticky as such on the hydrate surface, right?
Yes, I think this is a new concept that we have introduced to this community maybe a couple of years ago, right? And I think there is still some, to me, there is no doubt about it, but of course, I think not everyone is on board with this way of looking at gas hydrates, right? But water is the culprit for everything that happens in gas hydrate, right? And anyone can do this very simple experiment that we have done in the lab and we have demonstrated. You know, you take 2 ice cubes, right? And you make sure that they are dry, okay? Form them at a very low temperature and put it then in the oil, and then they are not going to stick. But if you make this ice cube at a fairly mild condition, very close to 0 degrees, and you keep it at the temperature, then you're going to have some water at the surface. It's not going to be converted, and they're going to stick. Okay. Think of hydrates as sponges, okay? And they're formable. Right? So if under shear, if you squeeze their sponge, the water is going to come out, right? But if you don't, then the water is just going to remain inside. Then if the water doesn't reach the surface, then the hydrates have nothing to, essentially, the water is the glue that makes the hydrate stick. Okay. We are basing this on our common knowledge that we have about what happens in any other system, right, where you have water present.
Yeah, got it. Yeah. So nice. Yeah, got it. Ramesh, you have anything to say?
Yeah. Thanks, Sum. I think it was a very interesting talk. So I just have one question on the morphology. So you were just showing a nice tube where the hydrates are getting formed. So it's pretty interesting. The question is, like, if you just consider a soil medium or a geomaterial, it will be consisting of a series of complex network of tubes, something like this, right? So, have anyone tried to capture how the morphology is getting formed in these sort of a tubular or a capillary connectivity structure? And that's one thing. The other thing is, it's apparent that the hydrates are just forming around the contacts first and then trying to grow inside, right? So this is also giving an idea that there is first some sort of a cementation between the grains that's happening, and then slowly the pores are getting filled. So
Yes.
that is very interesting, which also gives an idea that how the hydrates are stable, and we can discuss more on the morphology. But coming back to the question on the formation of these hydrates in this complex porous structure, people looked at it. That's my question.
So yes, a very, very nice question. Thank you. I think it all depends, again, go back to what I was emphasized, it all depends on how you form the formation conditions. And a lot of this unexpected morphology that I showed you is induced by shear, okay? And the pores that you're talking about in sediments, you're not going to have much shear, right? It's going to be very much like a static system. And so the process and the way that the hydrates are going to form is going to be very different. But I would still emphasize that the hydrates that are formed are going to be somewhat porous. Maybe not as porous as you see in here, right? Because this is there's a significant amount of shear that's imposed, right? But this porous structure that you still can think of a sponge, right, will facilitate the water transport through whichever the initial layer of hydrates is formed, right? Water transport. So it is always the water that's going to be moving, not as much as the gas. Right? So think of a pore, and you have water in one side and gas the other. You initially form a hydrate in that interface. And so to continue hydrate growth, water or gas is going to have to be transported in one way or the other. Most likely is the water that's going to be transported, okay, through this hydrate film that you form that is porous, right? Because it is much easier for the water to get through than the gas to get through, right? Gas doesn't like water, right? The hydrate likes water. So water is going to make it, right? So that's an important consideration if you're thinking about how to develop your experimental system so that you can form hydrate, right? Especially when you don't have shear in the system.
So the next question I'm just interested in is, like, you talked about shear. So essentially, like in reservoir, you don't have sort of shear, but like when you start doing some sort of shear, do you think there is some sort of a dissociation that will accompany, like during some sort of a large shear that's happening? I'm talking about the reservoir shear, not the shear you discussed, but I'm just saying.
Well, the shear that I'm talking about in here, right, are of the fluid phases, right? The shear that I think you're asking, it is related to a reservoir, so would be between solid plates, I would say, right, the sediments. I think it all comes down to where you are in the hydrate stability zone, right, in terms of temperature and pressure. Is the shear sufficient to induce heating or changing the pressure to destabilize the reservoir, right? That's, I think, what you need to consider, right? If it is not, then there shouldn't be any dissociation, right? The hydrates will remain stable. That's my answer. Yeah.
Yeah. So, Chandra, do you want to take a few more questions?
Yeah, I think there are many more, but in the interest of time, we are going to take a couple more from the Q&A box here. So one of them is asking you, how much will knowing the shear parameters influence on hydrate formation? How much will that reduce the inhibitor consumption cost?
Great question. I think this is one that has a lot of relevance to what we are doing and to what we are telling also our industry sponsors of how they can manage hydrate. In what we know and what we have seen, you can actually eliminate all the chemical injection and just rely on the shear, the hydrodynamics of the system in order to disperse hydrates. You can create a very finely dispersed hydrate system, just like I showed you in this video in here, under the right set of conditions. So to me, in the way that I describe hydrates in terms of their transportability, you can get any kind of outcome depending on the shear. What is that shear that we end up with this set of conditions? I cannot tell because it's very system dependent in terms of the temperature, the pressure, how much water, how much oil, what type of oil, and what are the actual flow pattern, right? So it's very complicated in a way that's great because it keeps us doing the research, right? But at the same time, to answer the questions, yes, you are able to control that. And even with the chemical additive, I would say that doesn't, just because you are putting a chemical additive doesn't mean that it is going to work the way that you expect. It depends on shear as well.
Thank you, Professor Sum. So the final question we'll take today is asking how much deviation can we expect in terms of the mechanical properties between naturally formed gas hydrate sediments and the synthetic ones that are formed in the laboratory?
Great question. Yes. I think, again, it depends on how you design your experiment to try to form the gas hydrate. I mean, the advantage that nature has, the ones that we find in the natural environments, is that it had, again, millions of years to be at how they are today. And we, of course, going to be very hard to mimic that, right? In terms of annealing. So maybe it's not necessarily that important that we try to do and get exactly the way that it is in nature in the lab, but we get as close as we can, and we consider the possible variations in the lab, right? And take that into account when we try to interpret the results, so that can be translated to what we might observe in the lab, right? I think we never are able to do as well as nature, but as scientists and as engineers, I think we can observe trends that can be well translated to what actually happens in the real world.
Thank you once again very much, Professor Sum. It was a very insightful presentation. And as you can see, there's a lot of interest, lots of questions, and maybe people will reach out to you after the talk with some of these questions.
I'll be happy. And if there are some questions that I didn't get to here and you want to send me that by email, I'll try to address them if you have a contact, or I can send the answers to you and you can reply, then forward them to the proper person. Sure.
Yeah, we'll try to make note of the questions and then send them back to you, after the talk. But yeah, once again, thank you very much for accepting our invitation to speak at the series. And it was a pleasure listening to you today. Hopefully, we'll stay in touch as our center grows, and we'll be able to learn from your expertise more. Thanks.
Thank you. Have a good night there.
Thanks. You have a good day too.
All right.
Thank you, Professor Sum, again.
Thank you. I appreciate the opportunity.
Thank you so much.